Let us talk about this problem. We are given a number n. Our task is to find factorial of n. What is factorial of n? Factorial is defined for input greater than or equal to 0 and it is multiplication of all numbers from 1 to n. For example, if n is 4, then our output is 24. It is 1 into 2 into 3 into 4, which is 24. For n is equal to 6, it's 720. 1 into 2 into 3 into 4 into 5 into 6. For n equal to 0, our factorial is 1. For n equal to 1 also it's 1. In general, we can say factorial of n is 1 into 2 into 3, multiplication of all numbers till n, and it's defined for numbers greater than or equal to 0. Now please pause this video and try to write down a function that takes an input number n and returns factorial of it. Let us first talk about an iterative solution to find the factorial. Later we will talk about a recursive solution. So the idea is super simple. We have a number n, we need to multiply all the numbers from 1 to n. So we initialize our result as 1. We go from 2 to n and multiply every I with the result. So finally we have multiplication of all the numbers from 1 to n. And if you see this example n equal to 5, we have initially result as 1. When I is 2, result will become 1 into 2. For I equal to 3, result will become 2 into 3. For I equal to 4, result will become 6 into 4. For I equal to 5, result will become 24 into 5, 120. What is the time complexity of the solution? This solution is simply having a theta n loop. This loop mainly runs n minus 1 times. So the time complexity of the solution is theta n. And how much auxiliary space it requires? It's not creating an array or any other data structure of size n. It's simply using constant excess space. So this auxiliary space requirement for this solution is big O of 1. Now please pause this video and try to write down a recursive solution to find factorial of a given number. Here is implementation of the recursive factorial function. The idea is simple. To compute the factorial of n, we can do it recursively. We can compute the factorial of n minus 1 and multiply the result of this recursive call with n. And that's how we can get factorial of n. So that's what we have done here. We take a number n and we multiply it with factorial of n minus 1 to get the result. Now when you are reducing n by 1, for example n is 5, you will reduce it to 4, then 3, then 2, then 1. So there will be a point when you reach 0, right? You will always reach 0 and our assumption here is n is greater than or equal to 0. This function is not going to work if you pass a negative number. So we have a positive number or a 0, and if you have such a number and if you are reducing it by 1, you will ultimately end up with 0 whatever input you provide with this assumption. So when you reach 0, you simply return 1. That's the base case for recursion. So when you begin with factorial 5, what will happen? It will call for 5 into factorial 4. So it will mainly call for factorial 4, wait for the result to come so that it can multiply it with 5 and return the result. Factorial 4 will wait for factorial 3, 3 will wait for 2, 2 will wait for 1 and 1 will wait for 0. When the control will come here, it will fall into the base case and it will return 1 to its parent, and parent will take this 1, right, and multiply with this 1, and parent will return 1 into 1 to its parent. And now factorial 2, what it will do? It will do 2 into 1. So it will return 2 here and this expression will be replaced by 2. So factorial 3 will return 3 into 2, 6. Now factorial 4 will return 4 into 6, 24. And factorial 5 will return 5 into 24, 120. So that's how you get the factorial 5 using this recursive function. Let us now talk about time complexity of this recursive solution. So I can write the time complexity recursion formula as Tn equal to Tn minus 1 plus theta 1. You pass a variable n, it makes a recursive call for n minus 1 and then it does theta 1 or constant extra work, which is checking this condition and doing the multiplication. So I can make a recursion tree of this recurrence like this, theta 1, theta 1, theta 1, theta 1 work that you are doing at every level, and this level is for n, then for n minus 1, then for n minus 2, and at the end you have for 0. So how many levels we have? We have n plus 1 levels, and how much work we are doing at every level? Constant work. So n plus 1 into constant is theta of n. So this solution, this recursive solution also takes theta n time. But if you compare it with the iterative solution, the iterative solution was theta n, but it was taking theta 1 auxiliary space. But this recursive solution is going to take theta n auxiliary space, because there will be a moment when you will have n plus 1 function calls in the function call stack. When you call for 0, right, you will have all the function calls in the function call stack, and these n plus 1 calls will take theta n auxiliary space. So this recursive solution requires theta n time and theta n auxiliary space. Also, this recursive solution causes extra overhead. That's why our previous iterative solution is considered better.